Thank you very much, and good morning to everyone. So, as you said, I'll be talking about some recent work we've done with the study of equilibration in low energy heavy ion collisions, and we all know that equilibration, dissipation, fluctuations are all interrelated network of observables. So. And in addition to that, the study of equilibration is relevant for the equation of state simulations and symmetry energy, and they are useful in modeling such phenomena. So since I assume this is for a general audience, so I'll briefly talk about the some general aspects of low energy heavy ion reactions and give a very short brief description of the tools that we use to study, perform these studies. And then I will focus on individual reactions to study equilibration phenomena for individual systems and discuss the things that affect equilibration, like the dynamics and shell effects, etc. And then at the end, we will try to make a more systematic study by introducing a scale measure and use it for many systems to try to extract these equilibration times. Okay, so for those of you who are maybe not familiar with low energy heavy ion reactions, this is a sort of gives you a view of the time scales of reactions, and naturally equilibration is related to the time scale of the reaction. So here we have the time axis goes this way, and this is time after the contact of nuclei, how much time has elapsed after nuclei came into contact with one another. And as we see, sort of the deep inelastic reactions, called deep inelastic reactions, are sort of high-end 10 to the minus 22 to mid to high-end 10 to the minus 21 second interval. The quasi-fission is from sort of high-end 10 to the minus 21 into 10 to the minus 20 seconds. And then you have a phenomena called fusion fission. This is a fused nucleus that has excitation that fissions due to its excitation. And then if you survive all this, you end up with a compound nucleus, and then that decays with neutron and gamma emission, etc. Right? So these are longer time processes. One thing to emphasize here is that beyond the deep inelastic regime, we essentially lose all total kinetic energy, translational kinetic energy. In other words, when you have two fragments at the end, going out, these don't carry any of the initial translational kinetic energy. They're just coming apart with the energy of the dynamics and Coulomb repulsion. And this is called Viola systematics. They're well described by the systematics. So in addition to this equilibration process, and of course the inelasticity of the reactions also increase as we go longer and longer in time. So the tool that we're going to use to study these collisions is based on the density functional theory and energy density functional. So let's look at the static outline first. So you have a many-body system that interacts with 1, 2, 3 body interactions. And in the density functional theory, we translate into a system where each nucleon feels the average field generated by all the other nucleons. This is also called mean field. And the exact many-body wave function Hamiltonian is now transformed into a wave function, many-body wave function, which is a Slater determinant and an effective Hamiltonian. And if we use these to calculate the energy, of the system, we find that it can be written as, for most effective interaction, it can be written as a volume integral of some quantity. And this is why this is called the energy density. And as you see, the energy density is a function of various things like rho, the kinetic energy, spin currents, spin tensor, etc. And you also have the Coulomb interaction. And of course, this is much more complicated than the case in the condensed matter physics, as we see. And so all these quantities are computed essentially from single particle states. So that's the essence of density functional theory. So just to show this briefly, this is the Skyrm energy density functional. And you can see there are time-odd terms, which are the bold ones in this Hamiltonian. And there are two things to point out. And one is that for these density functionals to be used in a time-dependent equations, they have to be Galilean invariant. And this is Galilean invariant by construction. Another point is that in the static calculations for even nuclei, the time-odd terms are generally zero, but for in dynamic calculations, they are not. So they enter into the dynamic calculation. All right, so so the generalization of the density functional theory to the time-dependent case is called time-dependent density functional theory, or TDHF. And here, describing taking the system from some time t1 to a sometime t2 is accomplished by using the time-dependent least action principle. So you construct the you construct action and the variation of action set to zero, then gives you the time-dependent equations, single particle equations. There are a couple set of equations, including this single particle Hamiltonian. So this corresponds to the most probable path between going from T1 to T2. And important thing is that only input into these calculations, the energy density functional, which are fitted using the structure information only. So the dynamics does not contain any free parameters to adjust, or not. These interactions, density functions are not adjusted to the collision phenomena. Okay, so few points about the codes. So modern time-dependent density functional theory codes are highly accurate and sophisticated. Our in-house code has these properties, like based on basis splines, 3D Cartesian, incomplete EDF is used, and encoded in such that it can take full advantage of, say, OpenMP processors on modern computers. Older version of this code, which has been highly modified, and instead of basis spline uses the fast Fourier transform method, it's called Sky3D, has been published in Computer Physics Communications and updated, and this is widely used by many people in doing these kind of studies. So the numerical, the emphasis here is that problem with numerical accuracy and simplifications due to numerical complexity and stuff are all taken care of. So there's these codes basically just use the given energy density functional to calculate the full dynamics. All right, so finally, a word about the initial approach, initial setup. Naturally, we cannot start the nuclei from infinity, and we don't have to, because we know that the nuclei only feel the Coulomb force when they're far apart. So you assume that the nuclei arriving to some distance in the numerical box on a Coulomb trajectory. So you take a separation like 30 Fermi separation initially, and then you compute the velocities they would have arriving on a Coulomb trajectory. Then these nuclei are boosted with these velocities, and then rest of the collision is then taken care of by the TDHF equations dynamically. And in the final state, if you have only one fragment, if these things come together and never come apart, that's called fusion. And if the final stage contains two fragments, you either have deep inelastic or quasi-fission. Okay, or it could be quasi-elastic too, of course. So I'm going to give you an example. This is a quasi-fission case of calcium-48 on 249 berkelium. And this is an ECM 234 MeV. And there's an impact parameter of orbital angular momentum L equals 60 h bar initially. And as we also see that this berkelium is highly deformed. So there's another parameter here, which is the orientation of the berkelium compared to the collision axis. And here, measuring from this direction, we have at 135-degree orientation. So the next movie is going to show you this collision. So this looks like a fast movie, but it's actually made to run fast because of time restrictions. So so the final fragments here, we started with calcium-48. You have 94 strontium and 203 gold are the final fragments. So you see there's a large transfer of particles. The contact time is 4.8 zeptoseconds in this reaction, which is 4.8 times 10 to the minus 21 seconds. And it takes 1.5 days on a 20 processor workstation running in OpenMP to actually compute this one particular collision. So this is all done with the TDHF equations. There is no external interference into any of these. Okay, so now that we have some basic knowledge of the tools that we use and what goes into them, let's start discussing equilibration dynamics. So we are going to be looking at equilibration of mass, isospin, energy, angular momentum, and fluctuations. And the fluctuations, of course, require us to go beyond the mean field. As we said, that gives us the single path. To discuss fluctuation about the average value, you need to go beyond TDHF. And then in the context of equilibration, since we're dealing with a dynamical problem, we also need to examine effects that influence equilibration. These are the time scales of the reaction, the length of time the nuclei are in contact, and orientation of deformed nuclei, as we'll see. And also, since we're dealing with a quantal system, what also influences equilibration are shell effects. So therefore, these are all, I'm going to give you some brief examples of these before going into the discussion of these. And just like to point out that there's a review of TDHF that for those are interested in finding more about it in this paper. Okay, so the first example is mass equilibration. And for reasons to see later, is the appropriate reaction for this is quasi-fission, because as we'll find out that mass equilibration actually require a longer time scale. And so we discussed the dynamical and shell effects. So here I'm going to give you the first example of dynamical and shell effects. This is reaction calcium-40 and uranium-238 at 225 MeV. And what we see here, these movies play too fast, but so here we have one system where you have initially a tip collision where the final fragments are 78 germanium and 200 mercury. And in this case, we have L equals 40 H bar, and this is a side collision initially. And this is a very rare case, I wanted to point out, very rare case that we actually see an equal mass split. So it's normally you don't, it's very rare to see that in TDHF that is the system actually breaks up into two equal fragments, symmetric fission, symmetric quasi-fission, actually. So what's plotted here is the charge of the heavy fragment versus the initial orbital angular momentum. So we see that for the side orientation, you have region where you actually have fusion, and beyond L equals 40, then you have a large mass transfer and long quasi-fission times. And then afterwards, it rapidly goes up towards the quasi-elastic regime. Whereas in the side orientation, you see no fusion, and the quasi-fission times are relatively short. And you see that the mass transfer is dominated a lot by the shell effects for this system. So you see that a lot of the particles are around Z equals 80, especially in low L value, is around the lead region. And so this is one example of how both the orientation effects influence the time scales of the reaction, and how the shell effects influence also the equilibration process. So recently we have undertaken another study of another system. It's calcium-48 on berkelium-249, the movies you have seen earlier, at 234 MeV. And we have actually done the most comprehensive quasi-fission calculations for this system. We have changed this orientation angle in 15-degree intervals from 0 to 180, and for each orientation did a full range of initial orbital angular momentum, which is about 12 L values. So I ended up with about total of 148 collisions to obtain the systematics from that. And in noting that each run takes about 1 to 3 days, this has been a sort of a all summer long computation. All right, so one plot you can do, and we have lots of results for this, but for the purpose of this talk, I'll just give a few of them. So you can see here for this system, the yield, what we call yield histogram, and a K density plot over that is a function of Z, the charge number or the fragments. So one thing to note is that we don't seem to be seeing for this system the Z equals 82 influence as much as in the heavy fragment. And then I'll come back to that in a second again, the next slide perhaps. But we also see that the dip inelastic and quasi-elastic peaks are distinctly separated from the quasi-fission area here. And of course, for this case, we don't have any symmetric breakups. So normally, experimentally, fusion fission fills up the center part mostly. All right, so so that was missing here. The in terms of the shell effects, we haven't seen the z equals 82 effect in this for this system. And here's another collision. This is just using different graphics with some internal density structure. But to note is that the final fragments are zirconium 99 and iridium 198, reasonably long contact time, or not too long, but it's 8 zeptoseconds. So very deformed zirconium-like fragment coming out here. So then if you plot these yield curves again, and just not the histogram, but the regular density curves, and try to see what shell effects you can see here, we see that we have the 82 line is up here, and then the neutron size, you have 56 and 126. And the yellow curves are taking all the data into consideration. And this is the central mass angle of the fragments versus the N and Z on the top lines here. So like the experimentals, we can actually set gates. And then we said, okay, well, let's see if we're going the backward and forward particles most. Let's gate on those and see what happens then. And that represents the purple region, purple curves. And what we really see again is that, well, no matter what you do, the 82 seems to be not exactly there. Neither is 126 really. It's close, but not exactly on top of it. But more predominantly, you see N equals 56 in both cases seems to be an influencer in these breakup reactions. So what we have really observed is that actually the and z equals 40. I didn't put a line here for some reason. The zirconium, neutron-rich zirconium isotopes seem to have the most effect in the determination of the fragments, which is something we have also seen in the calcium 48 on uranium 238 reactions. And structurally, we know that neutron-rich zirconium isotopes are highly deformed and very strongly bound. So this actually does make sense somehow. It's the deformed shell effects that are coming into consideration. One always tends to look at the heavy system as the driver of the fragment charge and mass, but it could also be the lighter system. So that's something to look more into. All right, so equilibration. So if you take all these results and say, okay, let's plot the mass difference, final mass difference over the initial mass difference. So this is the mass difference of the final fragments divided by the initial mass difference. And you see here, if you put all these plots, you see this is the quasi-fission region, and you see sort of a trend of things going down as the contact time increases. So you can either fit some, assuming a certain distribution, exponential distribution, you can fit and try to extract a time, or on the ballpark, you can say, okay, well, maybe 6 to 12 region, up 10 region, 12 region, that the things seem to sort of saturate and become flattened out. And that would be the time scale for mass equilibration. Now you can plot these. A more striking plot is to plot the mass ratio. So this is the mass of the fragment divided by the total mass. And as you see, you have the light fragment and heavy fragment, and you can clearly see that the curve flattens out after 10, 12 Fermis for this particular system at this energy. Okay, so this is a nicer plot for looking at that. All right, so so in summary, the mass equilibration seems to take something on the order of 12 and larger zeptoseconds, and there were actually older phenomenological and experimental studies of this kind of phenomena. And we have seen that orientation dependence affects the time scales. So you have slow quasi-fission versus fast quasi-fission depending on the orientation of the deformed nucleus. We have seen different kinds of shell effects. For these systems, we have seen that the lead 208 seems to have a major influence in the fragment formation. And this was actually, they actually measured experimentally the charges of the fragments, and it was centered around 82. That was determined too. And for the other system, we saw that we have some deformed shell effects and preference for neutron-rich zirconium isotopes was the general tendency. Okay, so that was for the mass equilibration. Deep inelastic reactions, of course, we know that these are intimately related with the symmetry energy and isospin dependence of equation of states, and usually we have much faster equilibration times for these. There was an experiment a couple of years ago at the Texas A&M group that at higher energy, at 35 MeV Fermi energies, which established about a 0.3 zeptosecond equilibration time. So we need faster reaction mechanism than quasi-fission for this, of course, and the right avenue for that is the deep inelastic collisions that to look at. So here I'm going to show you, just for the isospin transfer, a short movie. In this case, the system actually fuses, but what is shown here are the neutron and proton currents. And the upper half shows the protons and the lower half shows the neutrons. And I'm going to play the movie. And the thing to observe is that there's an initial transfer of protons one way, neutrons the other way, etc. And then as the system hangs together longer and longer, you see backwards, forward transfer, which eventually would equilibrate if the system had stuck long enough together. So, but it usually does not, in a deep inelastic reaction, it doesn't stay long enough to be fully equilibrated. So, and so here, let's see. So you see, initially protons were coming from tin to calcium, etc. And then as the time goes on, you get back and forth, things going back and forth, and trying to equilibrate itself. So this is a very interesting phenomena. You can see this is a very exotic system, but you can see that in all the reactions. And so, and in this case, the system fused. So in order to look at the isospin dependence, initially we said, okay, let's look at some reactions of krypton on lead. We actually had two krypton 78 and 92 at 8.5 MeV per nucleon. And we did a lot of deep inelastic calculations for these. And you see here the projectile-like fragment as a function of contact time, and plotted as n minus z over a, sorry. So it's n minus z over a on the vertical axis of the fragments. And versus the contact time. And contact time, as I said earlier, it is defined from the point the systems touch to the point where the systems are detaching. And you can define some nuclear density like 0.07 nucleons per Fermi cube or 0.08 nucleons per Fermi cube as your reference point, and determine that. And it doesn't, the results don't seem to depend exactly on what you choose, as long as it's something that's not too extreme. Okay, so so this plot is similar to actually what the A&M people had done for at a higher energy. So they had fitted an expression like this, and to find the 0.3, and here we found about 0.5 if you take this as the distribution, or if you do it a ballpark, you can say, okay, probably 1 or 2 Fermis over C. After that, things seem to saturate, and so equilibration times at lower energies are longer than the ones at the high intermediate energies, it looks like. And so there's another plot of how things actually how things move on this sort of the chart, if you wish. So if you plot the neutron number of the projectile-like fragment and the charge of the projectile-like fragment, where krypton initially sits around here. So what you find is that these are very quasi-elastic reactions here. So then when you more strongly damped reactions end up, these are the primary fragments, and end up coming down closer to the N over Z of the compound nucleus line. So this is the beta stability line, and this is the N over Z over the compound nucleus, which is like 1.42 or something like that. But they never reach there. So they never reach the compound nucleus N over Z value. Now these are primary fragments, and we actually calculate the excitation energy, then average intrinsic orbital angular momentum, and we know the neutron and proton numbers of these fragments. So we can go to a code like Gemini and use the other parameters as the default values, and see where these primary fragments end up. And as you see, they end up closer, eventually ends up to the beta stability line, most of them. And the ones that are far away usually are the more neutron-rich products. So here we have, all right, this is the same plot. I'm going a little fast, but this same plot for the neutron-rich krypton nucleus, both plots combine into one. So here you're starting with a krypton which is already close to the N over Z of the compound nucleus. So the primary fragments don't go very far. And the evaporation, they stay further away from the beta stability line, because in this case, you get most of the fragments end up being neutron-rich versions of their corresponding nuclei, and therefore they're further away from the beta stability line. So these are all interrelated quantities to the equilibration. And how about TKE equilibration? This is translational kinetic energy. So here we have 2 different systems. Again, we have our krypton on lead. Now, krypton is deformed, so you can also have 2 different orientations. And then we have nickel 58 on nickel 60 at 3 different energies. And what you see, then this is the effect of deformation. These are spherical, so they have more smooth behavior at shorter contact times. But you see that the TKE and the falls off in a nice sort of a step function way in this case, and more smoothly in this way in this case. And as you see, the small contact times, of course, correspond to more peripheral collisions. And then as larger contact times correspond to more dissipative collisions, deep and elastic, more collisions. And so it's nice to see that, you know, the equilibration happens when nuclei actually stay together longer, right? So from that, you can conclude that about 1.5 zeptoseconds, etc., could is sufficient to reach full energy dissipation. All right, so then we said, now we've seen examples of a few systems. So we said, is there a way to introduce a scale measure to make a study of many diverse systems so that they all kind of fit under the same plot to have a more systematic study with diverse systems and very diverse range of energies, and actually using three different codes in the process. So and this was published recently, and that paper has a large supplemental part supplement that has lots of tables of all the ingredients that I'm going to be talking about tabulated. So so the scale measure we decided to choose is defined with this equation. So X is the quantity that you want to study, and so this is delta X. Tau then is tau is the contact time linked together. So the X is the quantity at certain time, and then X infinity is the asymptotic value, saturation value, asymptotic value, large contact time value, whatever you want to call that, and X naught is the initial value of this quantity, right? Now it turns out that you know, depending on the type of reaction, sometimes you can define an X saturation value that is the same for all the systems. And for some type of reactions, you have to do it for each reaction, define a separate X infinity. So here we see the isospin equilibration phenomena. And so that's I is the quantity that's X in the previous slide is I now, and that's the difference n minus 1 Z1 minus n minus 2 Z2. So the n minus Z difference between the two fragments is a function of contact time. And as you see, these are these 5 different reactions here, from calcium 40 to lead 208, krypton, calcium 40, calcium 48, calcium 40, nickel 64, nickel 58, tin 124. So very diverse set of reactions, and also multiple energies. So not all of them are single energy, but you have different energies in some of these systems. And as we see, there's almost like a universal behavior for all these systems for this quantity to smoothly come down as a function of contact time. And what we also plotted was that Texas A&M experiment from Jadel et al. That from that PRL, and that's the dash curve that seems to nicely also fit through this. This shows this similar trend here as the as all these calculations. And as we see, we never really reach, a lot of these systems don't reach exactly the zero delta I, because you in most cases you don't get a full equilibration of the system. So there is still some difference between n minus u of the fragments, and therefore they lie above the zero line there. So there's some remaining charge asymmetry, which favors different n minus e values in fragments because of different Coulomb energies. There is also a new review article on equilibration times published by McIntosh and Ianello recently. Okay, so then we choose to look at mass equilibration. We look at what we call mass asymmetry. So you have mass asymmetry A1 minus A2 of the fragments, applying to that formula. And so you have delta A, if you go back to the formula, delta A like that. And again, we have diverse systems at multiple energies. And we see, as we plot, we do see a trend of things going down. And this dash curve is again from actually an experiment from ANU, an earlier experiment where they assumed the Fermi type mass drift to calculate this distribution, and from sulfur 34 and thorium 232. And as we see, it seems to follow a similar trend, in other words, right? So this is reasonable agreement between the data and all these calculations. So, but you can see here that the things are flattening out. We said 12 for the last system, but it seems to be even longer. So you can safely say that after 20, things definitely have saturated, and so the mass equilibration seems to take a much longer time. So one thing to emphasize is that the infinity value, delta A infinity, we have chosen a single one for this system as being 0, which corresponds to the case of equal breakup of the fragments of the system. So most of them are lying above that because they're not really breaking up in equal fragments. All right, so here's the equilibration of the translational kinetic energy curve. So as you see, we have many more systems here at many different energies. So certainly the and multiple codes to emphasize too. So you're seeing again a similar trend that we saw for our individual systems earlier. And again, you can say, well, after 2 or so, the system seems to have saturated. So in this case, we actually do calculate the infinite value of the TKE for each individual system separately. So we see, and finally we look at the angular momentum loss. Now we define this as the initial orbital angular momentum minus the orbital angular momentum at the time they're coming apart. Tau is the contact time, and we see again a lot of systems, a lot of energies, and we see a sort of curve again flattening out in this region. There's always some odd things going, variations and stuff, but that that is still can be attributed to the different deformations, different orientations, etc. of these systems where or energies. So energies can affect. So they doesn't mean that it's not equilibrated necessarily, because they're spending quite a bit of time together. So again, so from that we can also conclude. So these, other than the mass equilibration, the other equilibration times seem to be all on the order of a couple of zeptoseconds of contact time. Now the fluctuations in trying to study fluctuations where you want to go beyond the mean field. So so that's the fluctuation defined is, say, the mass fluctuation would be the mass operator squared minus the mass squared. And you have the NZ correlations. These are well-defined quantities when you discuss fluctuation phenomena. Now, TDRPA, what it does is that it detects the curvature of the distribution around the average value. And it does that by assuming a Gaussian distribution. So for that reason, it's only limited to the study of symmetric systems. So that's why you see here all symmetric systems at few different energies. We seem to need more results. It's hard to kind of tell from this what is the time scale, at least from the TDRPA results. You can conclude that after sort of the three zeptoseconds, things seem to equilibrate or saturate, but systematics is not clear, mainly because there aren't too many systems here. But actually that turns out to be true, because there's another way to look at that. And that's using the stochastic mean field method. Now, these are calculations for 3 different systems. And in this method, you can actually follow in real time the evolution of these quantities. And you see that they're all flattening out about 800 Fermis over C, or 800 to 1,000 Fermis over C, which does correspond to about 3 zeptoseconds, if you convert that. So it's safe to conclude that the 3 zeptoseconds is what it takes. It has to be longer than the other equilibration, but it's natural that fluctuations take a little longer to come into, to be born naturally. So it's 3 zeptoseconds makes sense. So what did we learn? We learned from these studies that first you can have a measure and actually make a more systematic study. And we've seen that the mass equilibration requires a much longer time scale, about 20 zeptoseconds, whereas isospin at low energies seem to be on the order of 1 zeptoseconds, as well as angular momentum. Energy similar, and the fluctuation seems to be a few times longer than that, like 3 zeptoseconds. So, and of course, any more systematic can always help, but in some of these cases, we actually had a lot of results already. So I'd like to thank my collaborators and show up some of the references. And thank you very much for listening.
Okay, thank you, Sait, for the very interesting talk. Are there any questions? Vitek has raised his hand.
So, Sait, thank you very much for a very comprehensive talk. I do not understand what do you mean by time-dependent RPA, atop of time-dependent Hartree-Fock, because time-dependent RPA, right, is an approximation to time-dependent Hartree-Fock. You can derive it from there. But what do you mean by RPA on the top of TDHF?
Yeah, TDRPA is maybe it's a misleading name. It's really the Balian-Veneroni method. That's what they call TDRPA.
Okay, Balian-Veneroni. This is,
Yeah, the Balian-Veneroni method, where you're basically calculating the second order effects.
yes, that I understand.
Many
But
body.
so Sait, but could you simply, start your time-dependent simulations, okay, from different initial conditions, slightly different initial conditions. In this way, you could sample fluctuations.
Yeah, if you can find, yeah, I mean, in some ways we are doing that, right? Because like doing the orientation dependence or orbital angular momentum difference and all that, that kind of gives you a lot of results.
Right.
That's why we had those, the curves, but that's different than say you want one energy, one impact parameter or a spherical system, right? You get always the same result no matter how many times you run the TDHF
Sure,
for that.
Deterministic, yes.
Deterministic. And if you want to find how the quantities for that one particular energy and angular momentum have the fluctuations around that average, then the in some ways the stochastic mean field approximates what you're saying. It theoretically what it does is that it generates different paths by different initial occupations, but it's done built into the theory, so you don't actually have to do many runs. You can actually extract it out of one run. But in essence, that's what stochastic mean field does.
I understand. This is.
Yeah.
Thank you very much.
You're welcome.
Can I ask a question?
Sure.
Yeah. Apologies for missing much of your talk. The talk was declared for different times at different places, so it's a disaster from our side. My question follows up a bit in the VTEX direction. So my question is about dipole oscillations. So isospin shuffling between projectile and target during the reaction. If the period of those oscillations is much shorter than the time of the contact and disconnection, then it's you can make an average like RPA or something. But what about something which comes with a definite phase, and this phase gets frozen when the fragments separate? That you have on top of the mass evolution, you have a shuffling of isospin between the two nuclei that gets frozen when they disconnect.
Okay, I'm not sure exactly I understand the question.
So imagine so physically the two nuclei get in contact. Now protons rush one way or neutrons the other way.
Right.
Then they come to the maximum, then they start swinging back. And that happens on a time scale which is comparable to the contact time.
And
at the moment you disconnect, it's frozen.
Yes, yeah.
And this is, if you do RPA or something, you average over all, many periods or many phases. What about this being in phase with the disconnection?
Okay, you mean like the TDRPA, doing TDRPA on that?
Well, TDRPA, I think it will just average out, but I'm not sure.
Yeah, okay, maybe we should talk about this later on. It's an interesting question.
Okay.
Philomena posted a question into the chat. She's
right.
asking, shouldn't the EDF also contain scattering information in the fitting protocol for these reaction applications?
Well, that's a very good question. And it should, but nobody has undertaken that study yet. So the question is, you can think about simple input like the which may have been done in terms of say vibrations in a small amplitude limit phenomena like monopole vibrations and resonances and this kind of stuff. But putting input into the reaction in taking reactions in principle could be done, but it would really complicate the fitting process, because then you have to do many times the TDHF runs in trying to get to fit the parameters. In some sense, just relying on the structure information when the EDF seems to actually work quite well for reactions with no parameters. And so you need to find a certain observable, I guess, is the thing where you want to include in your fit that will be very sensitive to the time dependent phenomena.
Okay, thank you.
Does that answer your question? But it hasn't been done really, is the answer.
Mm-hmm. Yeah, Philomena says thanks.
Okay.
Okay. Yeah, I think we are out of time. Thanks again for the talk.